Imagine peering into the universe with eyes that stitch together hundreds of hidden maps, telescopes that turn scattered data into seamless cosmic tapestries. Stay tuned, because number 1 reveals a secret most never suspect. Revolutionary JWST has merged data from its near-infrared camera and mid-infrared instrument to create a single, ultra-deep field that reveals galaxies from the first 500 million years after the Big Bang. By aligning thousands of individual exposures across multiple wavelengths, scientists produced a seamless mosaic that captures faint infrared glows previously invisible. This composite not only shows the distribution of early galaxies but also highlights the filamentary web of dark matter scaffolding their formation. Researchers estimate the map covers an area roughly equivalent to the full moon, yet it peers deeper than any prior survey. The integration process required sophisticated algorithms to correct for instrument drift, cosmic ray strikes, and varying background radiation, turning raw data into a coherent portrait of the infant universe. As a result, JWST's merged map offers astronomers a powerful tool to test cosmological models and refine our timeline of cosmic evolution.
Combining Hubble's advanced camera for surveys and wide-field camera 3, the ultra-deep field stitch brings together over 2,000 individual exposures taken over a decade. Few people realize that this effort required aligning images taken at different angles, wavelengths, and even during varying orbital conditions to produce a single, high-resolution canvas. The resulting mosaic spans a region of sky about 1/10 the size of a grain of sand held at arm's length, yet it contains an estimated 10,000 galaxies, some seen as they were just 400 million years after the universe began. By integrating ultraviolet, visible, and near-infrared data, astronomers can trace star formation histories and identify faint dwarf galaxies that would otherwise be lost in noise. The process also involved correcting for Hubble's slight focus changes over time, a task handled by advanced deconvolution software. This merged map continues to serve as a benchmark for studying galaxy evolution and the large-scale structure of the cosmos.
Merging Gaia's astrometric measurements has produced the most detailed three-dimensional map of the Milky Way ever assembled. By integrating billions of precise position, parallax, and proper motion readings, the mission creates a seamless stellar cartography that reveals the galaxy's spiral arms, streams, and hidden substructures. Researchers estimate the map includes over 1.8 billion stars, each plotted with an accuracy down to a few microarcsecons, enough to detect the wobble caused by unseen exoplanets. The integration process required sophisticated cross-matching of multiple data releases, handling variations in instrument calibration and accounting for interstellar dust that can obscure measurements. This comprehensive star position map not only charts the Milky Way's shape but also uncovers remnants of dwarf galaxies consumed over billions of years, offering clues about our galaxy's formation history. According to scientists, the merged Gaia dataset is reshaping theories of dark matter distribution and stellar dynamics across the galactic disk.
Hidden within Spitzer's warm mission archives lies an infrared sky mosaic that fuses data from the IRAC and MIPS instruments into a continuous map of the Milky Way's dusty regions. This effort combined over 10,000 individual frames, each captured at different wavelengths between 3.6 and 70 microns, to reveal the hidden nurseries where new stars are born. By stitching together these exposures, astronomers produced a seamless view of giant molecular clouds, highlighting filamentary structures that trace the flow of interstellar gas. The integration required correcting for thermal variations in Spitzer's detectors and removing bright foreground sources that could skew the mosaic. The final product spans roughly 40% of the galactic plane, and offers unprecedented insight into how dust grains absorb and re-emit starlight, informing models of star formation efficiency across the galaxy.
Beyond expectations, the upcoming Roman Space Telescope will generate a massive wide-field survey that merges observations from its high-resolution imager and coronagraph to map dark energy's influence across billions of galaxies. Early simulations show that combining data from multiple filter bands will produce a contiguous map covering over 2,000 square degrees, a sky area roughly 5 times larger than the Hubble Deep Field. This blended dataset aims to capture subtle distortions in galaxy shapes caused by gravitational lensing, allowing researchers to trace the growth of cosmic structures over time. The integration pipeline must harmonize differing exposure times, correct for detector non-uniformities, and align images taken months apart. Once operational, Roman's merged map is expected to tighten constraints on dark energy's equation of state, potentially reshaping our understanding of the universe's accelerating expansion.
Deeply integrating Euclid's visible light imaging with its near-infrared spectroscopic data yields a comprehensive cartography of the cosmic web. By merging millions of galaxy redshift measurements with high-resolution shape maps, scientists can reconstruct a three-dimensional network of filaments and voids spanning over a third of the observable universe. This combined approach allows the detection of subtle clustering patterns that single-band surveys would miss. The processing pipeline aligns spectroscopic slices with imaging tiles, correcting for instrumental drift and atmospheric light distortions despite Euclid operating in space. According to mission planners, the resulting map will enable precision tests of general relativity on cosmological scales and refine estimates of the total mass of neutrinos. The merged Euclid dataset is poised to become a cornerstone for future studies of large-scale structure and dark matter distribution.
Incredibly, the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will combine nightly images taken over 10 years into a dynamic, time-domain mosaic that captures the evolving sky. By stitching together billions of exposures across 6 optical filters, the survey creates a seamless, multi-epoch map where transient events, supernovae, asteroid passages, variable stars, are tracked in context. The integration process must handle varying atmospheric conditions, seasonal visibility changes, and instrument upgrades, employing sophisticated image differencing algorithms to isolate genuine variability. The final mosaic will cover roughly 18,000 square degrees, effectively the entire southern sky, and will be updated annually, providing an unprecedented chronicle of cosmic change. Researchers anticipate that this merged, time-resolved map will revolutionize fields from cosmology to planetary defense, offering a living atlas of the universe in motion.
Surprisingly, Kepler's archival data has been reprocessed into a composite transit map that merges light curves from over 150,000 stars to highlight planetary signatures across the Milky Way's disk. By aligning and stacking periodic dips in brightness, scientists enhanced signal-to-noise ratios, revealing subtle transits that individual observations missed. This merged map showcases the distribution of Earth-size planets in the habitable zones of Sun-like stars, suggesting that such worlds may be more common than previously thought. The integration required correcting for spacecraft drift, detector degradation, and stellar variability, employing Bayesian frameworks to differentiate genuine planetary signals from noise. The resulting composite not only expands the known exoplanet catalog, but also provides a statistical landscape for future missions targeting nearby habitable planets.
Remarkably, the Transiting Exoplanet Survey Satellite, TESS, has compiled an all-sky atlas of variable stars by merging short-cadence observations from its 4 wide-field cameras. This effort stitches together millions of light curves into a unified map that highlights pulsating, eruptive, and eclipsing stars across both hemispheres. By cross-referencing data from overlapping sectors, the atlas improves period determinations and uncovers long-term trends invisible in isolated datasets. The integration pipeline corrects for instrumental systematics, scattered light, and differing observation windows, delivering a coherent catalog of stellar variability. Astronomers use this merged atlas to probe stellar interiors, calibrate distance ladders, and refine models of stellar evolution, making it a valuable resource for both professional and amateur observers.
Finally, the planned Lynx X-ray Observatory aims to generate a high-resolution sky survey that merges data from its microcalorimeter array and high-definition imager into a single, ultra-deep X-ray map. By combining thousands of pointings, Lynx will produce a contiguous mosaic covering hundreds of square degrees, revealing the faintest hot gas structures in galaxy clusters and the intergalactic medium. The integration will involve aligning subarcsecond images taken over years, correcting for detector gain variations, and removing background flares. Expected to detect sources an order of magnitude fainter than current X-ray telescopes, this merged map will enable precise measurements of black hole feedback, dark matter distribution, and the thermodynamic history of the universe. While still in development, Lynx's combined survey promises to transform high-energy astrophysics.
We've traveled through 10 incredible telescopes, each one weaving together countless observations into a grand, unified portrait of the cosmos. Seeing how these instruments combine data reminds us that the universe is a mosaic, and every new piece reshapes our understanding. If you enjoyed uncovering these hidden connections, subscribe so you don't miss the next mind-blowing list we drop each week. Which telescope's map merging achievement blew your mind the most? Let me know in the comments, and if you found this journey worth your time, give the video a like. Thanks for watching, and keep looking up.